Today we are going to develop the background, okay, which will require us or which is required for the understanding of the residue theorem. Okay, now the residue theorem also provides us a technique to evaluate all those integrals which we evaluate using the Cauchy's integral theorem as well as formula. But the residue theorem is easier to be applied, or it is easier to solve the integration problems with the help of the residue theorem when compared to the Cauchy's counterpart. Okay. Alright. Now before we study the residue theorem, it is essential to know what residue is. Okay. Now residue is a term defined for series expansion of any function of a complex variable. Okay. Now unlike the series expansions of functions of single variable, okay, the series expansions of functions of complex variables have been divided into expansion with the help of Taylor's theorem, which is known as the Taylor series, and the other one is known as the Laurent series. Okay. Now in the Taylor series we only consider the positive integral powers of z minus z naught, including the zeroth power. Okay. Whereas in the Laurent series expansion, okay, or expansion of a function of a complex variable using the Laurent series, we not only consider the positive integral powers and the zeroth power, but we also consider negative integral powers. Okay. And the residue is the coefficient of the power 1 upon z minus z naught raised to 1, okay, which is usually denoted by b1, and this b1 is actually the residue. Okay, so we will talk about this in the next lecture, okay, how to find b1 or what do we mean by Laurent series and so on. So today we are going to discuss only the Taylor series part, okay, and the associated theorems. Okay, now the primary question when it comes to infinite series is when will the series converge? We have already seen this when we studied infinite series of real numbers, right? Okay, so this is what we are going to see in today's lecture. We are going to start with the geometric series, and we are going to talk about the convergence of the geometric series, and throughout our lecture, okay, we will assume that z is a complex number. Okay, so from now on we will not say z is a complex number, or in general the variable that is present in the series. Okay, we will say that we will assume that it is a complex number. Okay, so we will first talk about the geometric series and its convergence. Okay, and this will require us to know what absolute value or modulus of a complex number is. Okay, and then we will see why or how the geometric series is connected or linked to the already known Cauchy's integral formula. This has something to do with the denominator of the integrand present in the Cauchy's integral formula, and then we will see examples wherein we will find the region where the infinite series actually converges, okay, the geometric series. Then we will state the power series, or then we will define the power series, okay, along or expanded along the center, which is a complex number. Okay, it can be a real number, but it can also be a complex number. Okay, then we will present examples, okay, and then we will see two theorems. Okay, We will first see the converse of the Taylor's theorem, and it has two parts. Part 2 has something to do with the derivative and the integration of the function represented by the infinite series. We will first see the converse and then we will see the actual Taylor's theorem. This has real counterpart as well. Okay. Then we will see the Cauchy-Hadamard formula, which is useful to find the radius of convergence and the region of convergence of the infinite series. Okay, so these are the topics that I'm planning to cover in this lecture. The first topic, geometric series. Okay, now the definition of the geometric series is no different than what it was in the case of real numbers. Okay, so the geometric series consists of two parameters, the first term a and the common ratio r. Okay, but this time both a and r need not always be real numbers. A and r can also very well be complex numbers. Okay, so using the summation notation, we may write the geometric series as summation of a times r to the power j. You can take a common, as j runs from 0 to infinity. Okay, so j is still the summing variable which can take non-negative integral values. Okay, and the theorem that we saw in the real sense is also applicable here. Okay, so this theorem says if the modulus of the common ratio is less than 1, then the geometric series converges, and it converges to a upon 1 minus r. Okay, now here by mod we mean the modulus of the complex number. Okay, so if our common ratio r is such that its real part is x and its imaginary part is y, then we must have the complex numbers modulus, that is root of x squared plus y squared, the positive root, less than 1. Okay, and well, when does it not converge? If the modulus of the complex common ratio r is greater than or equal to 1, then the series diverges. Okay, or it doesn't converge. So let us now see two examples. Example 1 where it converges and example 2 where it doesn't converge. Okay, so let us consider the first question. Okay, wherein the function is I upon 2 to the power n, and n is taking the values from 0, 1, 2 till infinity. Okay, so by writing this, not using the summation notation, we will get the associated geometric series. And what will it be? I by 2 raised to 0, 1, I by 2 raised to 1, 1, I by 2 raised to 2 is I squared upon 4 or minus 1 upon 4, plus I by 2 raised to 3, I cubed is minus I, so it will be negative I upon cube of 2, that is 8, and then the numerators will then start appearing in the sequence 1i minus 1 minus I. Okay, so if you go to the fifth term, the numerator is going to be I to the power 4, the denominator is going to be 2 to the power 16, and so on. Okay, now you may observe here that this particular series is actually giving us two sub-series, if you want to call them. The first one is the real part of the series, and this real part is 1 minus 1 upon 4 plus 1 upon 16 and so on. Okay, and then this also has an imaginary part. Okay, this imaginary part is 1 upon 2 minus 1 upon 8 and then the subsequent terms. Okay, plus 1 upon 32 and so on. Now you may observe that both the real part and the imaginary part of this infinite series have the same common ratio, and that common ratio is negative 1 upon 4. The difference is only in the first terms. Okay, here it is 1 and there it is 1 upon 2. Alright, now let us apply the theorem to test the convergence of this geometric series. Okay, first term is 1, yes, Okay, now as far as the original series is concerned, what is the common ratio? The common ratio is I upon 2 or I by 2. What is the absolute value of R? 1. 1 upon 2. Yes, because absolute value of I is 1 or modulus. Okay, now is this less than 1? Yes. So according to the theorem, because the absolute value of the common ratio is less than 1, this infinite series converges, and we can now find the sum, okay, or S, the value of S. It is A upon 1 minus R. A is 1 and R is I upon 2. So we are going to get 1 upon 1 minus I by 2. You can simplify this, which will give us 4 upon 5 plus I times 2 upon 5. Okay, now if we compute these two sums, then these two sums will turn out to be 4 upon 5 and 2 upon 5 respectively. Let us check. Okay, let us try to find the sum of the real part. Okay, so this time it is going to be 1 upon 1 minus 1 upon 4, or 1 upon it is going to be plus 1 upon 4, because the common ratio is minus 1 upon 4, right? So it is 1 upon 5 by 4 or 4 by 5. Yes. Okay, now let us go to the second one. I think this has to be half of the first one, because it has the same common ratio, but the first term is 1 upon 2. Okay, so that is 2 by 5. Yes. Okay, so we have now got another result. Okay, if any infinite series converges to S1 plus IS2, okay, where S1 and S2 are complex numbers, then the real part of the expansion converges to S1, obviously, and the imaginary part converges to S2. Okay, and we have verified it for this particular example, and we may deduce that even if one of these two, S1 and S2, the associated series, even if one of them does not converge, then the original series also does not converge. Okay, all right, now let us go to the next example. So there is only one difference between this one and the first one. Okay, the difference is in the common ratio. In the example 1, the common ratio was I upon 2, and here in the example 2, the common ratio is I. Okay, now if we expand this, then we will get the terms 1, okay, I to the power 0 plus I squared, which is minus 1, plus I cubed, which is minus I, and then again this particular sequence will repeat itself. Okay, now because the common ratio is equal to I, its modulus is going to be 1. So this is not less than 1. So this clearly implies the divergence of the infinite series. Yes. Now, what do we know about the real and the imaginary parts of this series? The real part is going to produce the following series. Okay, let's call it S1. 1 plus minus 1 plus 1 plus minus 1 and so on. Okay, so this is an alternating series, and we know that the limit of the partial sums as n tends to infinity does not exist, okay, for this. And same thing applies to the imaginary part of this series as well, okay, which is again 1 plus minus 1 and so on. So for both of these two infinite series, in fact they are identical to each other, because the limit of the partial sum, okay, because this limit doesn't exist, the original infinite series also doesn't have any limit, okay, and hence we say that it diverges. All right, okay, so this was about the geometric series. Now we will see why are we studying this. Okay, what is the connection of the geometric series with the integration of functions of complex variable? This connection of geometric series with the integration of complex variable functions is through Cauchy's integral formula. Okay, so let me first tell you the Cauchy's integral formula that we studied, and then I'll tell you that I made a small change as far as the variable of integration is concerned. What was the Cauchy's integral formula that we stated? In fact, we proved it, right? Yes. So in the Cauchy's integral formula, we are given three things. Okay. First is function f of z, and it is known that this function is analytic in a simply connected domain D belonging to the complex plane. Okay. And we are also given z naught, which is a complex number, any complex number in the domain D. And the third thing that we are given is any simple closed path in D which encloses z naught. Okay. Now please note that in the Cauchy's integral formula, the integrand is not just f of z. Okay, that is there for Cauchy's integral theorem. Okay, so for Cauchy's integral formula, we deliberately introduce the factor z minus z naught in the denominator of the integrand, and the conclusion of the Cauchy's integral formula is, if we have these three things given to us, then the line integral of the function f of z upon z minus z naught taken along any closed curve, any simple closed curve in D which encloses z naught, this integral is equal to 2 pi I times the value of the numerator f of z at the point z naught. Okay, so this was the Cauchy's integral formula. Now I have modified it a bit. What I have done is, instead of using the variable of integration as z, I'm using the letter w. Okay, so the variable of integration has changed from z to w. Okay, and the point, it has changed from z naught to z. Okay, these are the two changes that I have done. Everything else is same. Okay, so now the Cauchy's integral formula can be stated as f of z equal to 1 over 2 pi I. Okay, so you can bring it here as well. F of z equal to 1 upon 2 pi I times the integral of f of w upon w minus z taken along any closed curve C or any simple closed path in D where the function is analytic. Okay, now look at the denominator of the integrand. Is it not 1 upon w minus z? Yes. Now this has some resemblance with a upon 1 minus r, which is the sum of the geometric series, if at all the sum exists, isn't it? We can always write this thing a upon 1 minus r as a into 1 upon 1 minus r, or we can also write it as 1 upon a minus r upon. Okay, so this resemblance actually encourages us to try to find the region of convergence or the values of z and w for which this particular series or this particular number 1 upon w minus z can be associated with a convergent geometric series. Okay, so this is how we can do it. There are two ways to do this. Okay, the two manipulations of the expression 1 upon w minus z. Okay, the first manipulation is very simple. What you have to do is you have to take w common from the denominator. So it is going to be 1 upon w times 1 upon 1 minus z upon w, which means the expression 1 upon w minus z can be associated with a geometric series when the modulus of z upon w is less than 1, isn't it? Because this is now like r. Okay, so when the absolute value of or the modulus of z is less than modulus of w, then this particular expression 1 upon w minus z can be associated with a convergent geometric series. Okay, this means z has to be closer to the origin than w. Okay, now let us go to the second manipulation, wherein we will not take w common but we will take minus z common. Okay, so if we do that, then this minus z will become 1, so let me write it first, and w will become minus w upon z. Okay, minus w upon z. Now this is also resembling a upon 1 minus r, but this time what we have here is w upon z. Okay, now this, if this resembles r, then from the theorem what can we say? We have to say that mod of w upon z has to be less than 1, or z must be such that it should have a greater modulus than w. Okay, or it should be further away from origin than w. Okay, so the same expression 1 upon w minus z can be associated with two different geometric series, okay, having different regions of convergence. Okay, the first manipulation applies when mod z is less than w, and the second manipulation applies when mod z is greater than w. Let us now see two examples of the same. Okay, for this we are going to introduce ourselves to a term from discrete mathematics known as the Z transform. Okay, so we are going to define this Z transform of a sequence f of k where k is any integer as follows. Okay, now we already know what sequences are, right? You can your definition of sequence is any function defined from the set of natural numbers to the set of real numbers, but now we are going to change it a bit. We are going to say that this particular sequence is a function which is defined from the set of integers to the set of real numbers or complex numbers. Okay, so we are going to define it as follows. The Z transform of this function is given by an infinite series which starts at minus infinity and ends, I mean, we cannot say that it starts at minus infinity. Okay, so k runs from minus infinity to plus infinity, so k assumes each and every integral value. Okay, and associated with each term of the sequence f of k, we have the power z to the power minus k. Alright, so if f of k is the sequence, to find its z transform, we will multiply f of k by z to the power minus k and we'll take the sum. Okay, now of course, this being an infinite series, we would like to know whether it converges for all values of the complex number z, or does it converge to some values. Okay, so let us now find that out. So I've considered two cases associated with each of the two manipulations. Question 1, find the values of z for which the sum converges. Sum means this sum. Okay, if f of k is given by the sequence f of k is equal to 2 to the power k if k is any non-negative integer, and f of k is equal to 0 otherwise. Fine, so this is very much like our sequence. Okay, we usually consider only the non-negative values while defining any sequence. Okay, now we will first use the definition and try to develop an expression containing z using the geometric series. Okay, first write down the definition. Definition of z transform is sum of f of k into z to the power minus k as k runs from minus infinity to plus infinity. Okay, now you observe that for all negative integers the function is taking the value 0. Yes, so for all values of k less than or equal to minus 1, f of k part should be taken at 0, isn't it? Yes, so there is no need to consider this now. Now go to the next part. Okay, so here what is f of k? 2 to the power k, which means as k runs from 0 to infinity, f of k should be taken as 2 to the power k. Alright? Yes. And 2 to the power k into z to the power minus k is as good as writing 2 upon z to the power k. Yes. Meaning this is now a geometric series. Okay. But note also that at the same time this is also a function of z. Alright, and because it is an infinite series, let's now try to find the region of convergence. Okay, use the formula. It is going to be 1 upon 1 minus r, but this formula will be applicable only when the r part, the absolute value of the r, should be less than 1. Okay, so if we want mod of 2 by z to be less than 1, what does this imply? This implies that 2 upon mod z should be less than 1, or this also implies that 2 should be less than mod of z, or mod of z is greater than 2. Okay, so this particular simplification of the infinite series, or z transform of the original sequence, you can take it as z upon z minus 2 only when mod of z is greater than 2. Okay, observe that here z is in the denominator and we have a constant in the numerator. Okay, now let's try the other example. In this example, what we have is, we have a similar looking expression, but this time what we have is, we have 3 to the power k as g of k if k assumes only non-negative integral values, that is k belongs to the set minus 1, minus 2, minus 3, so on till minus infinity. Okay, I mean, let's not write it. Yes, and for all other values of k, including 0 and the natural numbers, the sequence g of k is 0. Okay, so the question is saying find the values of z for which the sum converges. Use the definition of the z transform. Z transform of g of k is the sum of g of k times z to the power minus k as k runs from minus infinity to plus infinity. Okay, this time the part from as k runs from 0 to infinity will be 0. Okay, by definition of the sequence g of k, and for the negative values of k, g of k is defined by 3 to the power k, isn't it? Yes. So we now have the following thing. We are going to change the summing variable from k to m, and we are going to let k to be minus m. So if k runs from minus infinity to minus 1, m has to run from 1 to infinity, just because we are more comfortable with a positive summing variable. Okay, or a summing variable which assumes positive values. Okay, so this time what we should do is, we should replace k by minus m. Yes, and if we do that, it will be 3 to the power minus m and z to the power m. Okay, so this is now yet another geometric series. Okay, this time the first term is not 1, the first term is equal to z upon 3 corresponding to the m value 1. Okay, so expand it, you'll get z upon 3 for m equal to 1, then the square of z upon 3 for m equal to 2, and so on. So this is again a geometric series. Yes, it is. But more importantly, it is a geometric series as well as a function of z. And if we want to associate the closed form of this function to this infinite series, then we should put some restriction on the common ratio of this particular infinite series. Yes, what is the common ratio? The common ratio is z upon 3. by the theorem, what is the restriction that we should have on the common ratio? Mod of the common ratio has to be less than 1, or mod of z should be less than 3. Okay, and if this condition is satisfied, that is, if mod of z is less than 3, then we can have a closed form of the infinite series, and that closed form is first term into 1 upon 1 minus r, or z upon 3 into 1 upon 1 minus z upon 3, because here both the first term and the common ratio are same. Okay, and if you simplify it, you will end up getting the expression z upon 3 minus z. Okay, now observe that here what we have done is we have basically followed the same approach that we followed for our previous term. The only difference is here the z thing is in the numerator of the common ratio, and here the z thing was in the denominator. And it is now very much clear that the region of the complex plane for which the first expansion is valid is the region which is an open region mod z less than 2. Okay, and for this one it is mod z greater than 2, I should have said, yeah, mod z greater than 2, and here it is mod z less than 3. Okay, yes, I mean, now you can actually define a new sequence, let's call it h of k, and say that this is equal to f of k for k greater than or equal to 0, and g of k for k less than 0, and then for this the region of convergence will be the annular region between the circles mod z equal to 3 and mod z equal to 2. Okay, so the key point is you can, if you have a geometric series, and in particular an expression of the form 1 upon one complex number minus the other complex number, or a complex variable minus something, you can always associate a geometric series with it, provided you apply the theorem correctly. Meaning you mention the values of z for which the geometric series actually converges, and the condition is the absolute value r, the absolute value of the common ratio r has to be less than 1. Okay, fine. So if you were to consider the first infinite series, okay, it was applicable only when the absolute value of the complex number was greater than 2. If you consider the second infinite series, it is applicable only when the absolute value of z is less than 3. Okay, and the third one, which we considered now, you can its z transform will be valid only when the absolute value of z is between 2 and 3. Okay, so basically the intersection of the two regions.